Today's lecture will speak about shallow foundations. We have already studied before chapter 1, which is the description of the different types of foundations. Now we are going to concentrate on the shallow type of foundation. Shallow foundations means foundation that is on top of the ground. But really we cannot put the foundation on top of the ground for two reasons. The first reason is the surface part of the ground is usually disturbed, so I cannot just put my foundation on a disturbed soil. Second thing is that it will be affected by the environment, rain, hot and cold weather, sand, so it will be affected. So what should I do? I just bury it below the ground. Just go say 1.5 meter, 2 meters and put my foundations. It is below the ground, but we call it as if it is surface, but it's not surface, it is shallow. Shallow means that it is at a very near distance to the surface of the ground. The other is deep, it goes meters below the ground. So this is shallow foundation. This is the shape of the shallow foundation. I have a column. The column is connected to a foundation. The load comes from the column. The load is distributed all over the foundation. And then the top part of the foundation is called the PC. The RC, the reinforced concrete foundation, which is the part that includes the concrete and the steel reinforcement. Sometimes I can just, this is enough and I use this. But in many cases, I add something below it, which is a plain concrete mat. This plain concrete has many benefits. One of it is related to cost, because using this below the foundation reduces the amount of the reinforced concrete. And if I reduce the amount of the reinforced concrete, it is more expensive. So if I reduce the quantities, then I will get a final cost that is less. So this is one thing. The other thing, instead of putting my important foundation directly on the ground, and it would be contaminated by the ground, some of the ground would go inside the foundation, so I have to put something as a barrier between my important foundation and the ground below. So in all cases I will have to put, say, 10 centimeters of plain concrete on the ground to work in a clean environment. So if I'm going to put at least 10 centimeters, why not add another 20 centimeters or something, so that it would be good enough to work and to be considered in my foundation. So usually we do this. So it is either just 10 centimeters of plain concrete followed by my foundation, or no, I put, say, 30 centimeters, 40 centimeters of plain concrete, and I consider it part of my foundation to reduce the upper part, which is the reinforced part. This is just a quick introduction. The purpose of using shallow foundation is to convert the concentrated load from the column into uniform stress, so that the soil can bear it without collapsing or without failure. In order to achieve a uniform load distribution on soil, the foundation base must be able to bear and transfer the load to the soil. There are several types of and forms of rules to choose from according to. What are the important factors that we have to satisfy in our foundation, or to know about our foundation? Number one shape of the column or wall mounted on the base. Suppose that I have a column, and this column I have a foundation around it. It means that part of the foundation will be directly below the column, and part will be as if it is cantilever part outside of the column. The longer the cantilever, the more the moment. So it will be the depth will be increased and the amount of concrete will be increased. So I need to have the foundation with the minimum cantilever outside of the column. So if I have a column that is say 30 by 80, it is better to have the foundation, also the difference between the length and breadth of the foundation equal to the difference between the length and breadth of the column, so that the cantilever all around would be the same. If you have the cantilever very big in one direction and very small in the other direction, then it will be expensive, because the governing case will be the bigger cantilever. You understand what I mean? We will see it when we come to a plane. So one of the important things is the shape of the column. I have to know the shape of the column or the wall, because I can do a foundation for a wall. It's the same. Load of the column, the distance between the columns, neighbor, is there a neighbor next to this column or not? Because this column may be at the end of the land, and next to me is a neighbor. So in this case, my foundation will not be able to go inside the land of the neighbor. So I need to know the borders of the land or the extent of the land, so that I know that I have adequate space for foundation or not. I need to know the distance between columns, because if I know the distance between columns, then I know the space allocated for my footing. I cannot exceed a certain limit, and the load and the dimensions of the column. Components of shallow foundation. We said it as we were going, but we will just list them now. I have something called the RC, which is the reinforced concrete part. This is the main part of the foundation. It is the RC. It's similar to the PC or the plain concrete, but in addition it has rebars or reinforcement, and of course the quality of the concrete is higher. If you are using two different grades of concrete, then you put the better grade for the RC, and you put the lower grade for the PC. The second part is the plain concrete footing, which is a layer of regular concrete, normal concrete, placed under the RC and has several purposes. Why do I put it? As we said before, I need to work in a clean environment. To work in a clean environment, then I have to make a separation, a barrier between my RC and the ground. So I have to put something, this PC, to ensure that ground will not contaminate my foundation or will not go inside my foundation. The other thing is to, if I put adequate thickness, then I can depend on it to be part of the foundation. I can use it as part of the foundation, and in this case, you see here, you see this drawing, this is the RC, and this is the PC. If this PC is very small, very thin, actually all my, this one will have to increase, will be bigger, because it will take all of the load, and the other is just, consider it just a membrane, as if you are putting a membrane on the soil. But if you put something this thick compared to the RC, then I can use it, and I do some stress distribution. Let's follow what I mean. Here is the force P. This force, it will be divided into an area represented by this distance. So the load will be divided on this distance. It will give me a stress. This stress can be higher than the stress of the soil because it is not touching the soil, it is touching concrete. So if it is resting on concrete, then I can go with my stress higher than the stress of the soil. If this was the soil, then this area is not enough. I have to increase it. So by putting this concrete layer, I managed to increase the allowable stress instead of using the allowable stress of the soil to use the allowable stress of the concrete. Once I reached here, the stress will be redistributed again from this point to this point. So now the load will be divided on a bigger area. In this case, the stress should be the stress of the soil. So it is an interface. Adding this interface in between help me to decrease the plain concrete. If I just, on this cross section, I tell you, draw it, but suppose that this is 20 centimeter. I tell you, no, make it 40 centimeter. If you make it 40 centimeter, then in this case, your plain concrete, your reinforced concrete can be reduced more. So the steps is like this. I go with the load. I take the bearing capacity of the soil. I divide the load by the bearing capacity. It will give me an area. This area will be the area of the PC, not the area of the RC. So I will take this area at the beginning. Once I use this area, I go up with this inclined line, slope 45 degrees. And then I get the new area. In this case, the new area, it will give you a stress that is less than the allowable of the concrete. But this is the maximum you can take because I cannot extend my plain concrete outside of my reinforced concrete. You cannot have cantilever, because to have cantilever it means you have moment. If you have moment, then you need to have steel, but I don't have steel in the PC. So the maximum to go outside the reinforced concrete is just the depth of the plain concrete. I just give you an idea, but when we go to a section, you will understand it correctly. So now this is what we just have said. This is what we were discussing now. This is the PC. This PC can extend as much as you need, but if you extended more than this distance, there will be moment on this PC, and PC cannot take moment. So what will happen? It will crack. Once it cracks, it's not working. So I have to stop it earlier. I have to go outside the RC maximum this distance. What is this distance? This slope is 1:1. This height is the thickness of the plain concrete. So this also is the thickness of the plain concrete. So to use the maximum out of this PC, you just, once you get the required area of the PC, how to get the required area of the PC? The load divided by the bearing capacity of the soil. I get the area. So this area will be transferred into length and breadth for the PC. Now I can reduce the size of the RC. The maximum that I can reduce is to go from this point 1:1 to reach this point, and from this point 1 to 1 to reach this point. And once you reach this point, get the new dimension, and this is the maximum you can take, or the not the maximum, it is the minimum dimension that you can take for the RC in this case. So how to get the length of the RC? It is the length of the PC minus twice the thickness, because here is one thickness and here is another thickness. So the relation between this dimension and this dimension is one PC to the left, one TPC to the left and one TPC to the right. Okay, so this is the relation between LRC and LPC. The same for the B, length and breadth. Okay, so now this is the relation between the RC and PC in terms of length and breadth. Now we go into something called the shearing capacity or the shear strength. The goal of the design process is to find the dimension of the PC and RC and its area of steel. First, we must know the type of stresses on the foundation and the effect of each dimensional change. Concrete dimensions. Foundation area. By the way, this we have said in our description of how we design the foundation quickly. The first thing we do is to design the area. I get the load divided by the strength of the soil or of the material below to get an area. So this is the foundation area. I should not exceed. Not exceed. I should not go less than this area, otherwise the stress will increase. So this is the minimum area that I can use to help that the bearing capacity of the soil is not exceeded. The second thing is the thickness. The thickness resists the bending moment. So this is the second part of my first part is to get the dimensions, then the second part is to calculate the moment, and based on the moment we can calculate the thickness. This we'll see in the next slides. Once I calculate the thickness, then similar to any concrete element, we design the amount of steel. So, like what you do when you design a beam. To design a beam, you get the depth of the beam, and then once you get the depth of the beam, you get the amount of rebars or reinforcement you need. So this is the same that we are going to do. Area steel, which is the area of the rebar, the task of the rebars is to resist the bending moment. Steps to solve any problem. Any shallow foundation, this is what we have. I have P ultimate, the ultimate load of the column. In this, we have to say something that is very important. Usually, we either use the working load or the ultimate load, depending on the code that we are going to use. In Egypt, we have the code for the RC, for the design of the concrete elements. And we have the code of soil for the design of the soil elements, or the soil interface elements. Foundation is a soil interface element. The code of the RC is using the ultimate load, and the code of the the geotechnical code is using the working load. So we have a conflict here. This conflict is related to Egypt only because we are using two codes, so we have to use two loads. The first load, we use it, which is the working load, when we use the geotechnical code, and once we finish the task of the geotechnical code, we go to the structural code, then we have to change the load from the working to the ultimate. So, to get the area of the foundation, this is based on the geotechnical code. So I get the working load, I divided it, the working load, divided it by the bearing capacity of the soil, I get the area. So this is based on the geotechnical code. Now I need to calculate the steel. I go to the concrete, reinforced concrete code. It works with the ultimate load. So I take my working load, I multiply it by 1.5 to get the ultimate load, and then start calculating the depth of the foundation and calculate the steel. So to calculate area of the foundation, I use the working load because I'm using the geotechnical code. Then the next step, to calculate the depth of the foundation and the amount of steel, I have to multiply first the load by 1.5 to get the ultimate and go to the reinforced concrete code and design according to the reinforced concrete code. So this conflict is only related to this period in Egypt. Once they modify the geotechnical code or update the geotechnical code to use the ultimate load, we are not going to say this again. We use the ultimate load from the start till the end. But unfortunately, this is the only item in the building that we use two codes. That is the foundation, because I have to use the geotechnical code when I'm dealing with the soil, and then use the structure, the reinforced concrete code when I'm using getting the depth to get the rebar. Okay, this is very, very important and very confusing unless you put it in your mind before we start. You cannot just judge it when you see a solved example, because you are going to, why in this part you are using ultimate here, why you're using working. It is because of the environment that we are working in it, which uses two codes in the same time. Okay, so now it is the P ultimate, not the working. Before that we were using the working to get the dimensions, but now we are going to get the bending moment, which will be used for the steel and reinforced concrete. Then we have to use the ultimate load. Calculate the bending moment. How to calculate the bending moment? You have P ultimate, you have the dimension that you have already got from using the geotechnical code before. So you know the length and breadth. You just divide the load by the area, you get the stress, and then you have here a cantilever, WL squared by 2. You get the bending moment. So it is the bending moment related to the ultimate load. But we do not calculate bending moment according to working loads. So this is exactly what we have said now. Okay. Okay. Now, once I reach to the, I need to reach the bending moment on the foundation. Take into consideration that you have two bending moments, not one bending moment, because you have two directions. Each column has length and breadth, and each foundation has length and breadth. So you have a moment in the direction of the length, and you have a moment in the direction of the breadth. And you should get the bigger to design your foundation. If you have both moments equal, then you can design only one. How can you have both moments equal? If I have equal cantilever from both sides. So this you can take into consideration. Now, this is what is the shape of the moment. If I take a section here and take off the part of the foundation from here, then the part I just took off, it exerts a moment in this direction. The part similar to this one in this direction wants to bend up. So how can I prevent it from bending up? By putting steel below to prevent the portion of the cantilever from going up after the column. So now these are the dimensions. This is the shape that you should have reached. You now know that these are the dimensions of the column A and B, and you know that by dividing the load of the column, the working load, by the bearing capacity, you can get LRC and BRC, which is the area of PC. You get the area of the PC and the dimensions of the PC. Once you know them, you can go inside the thickness that you have assumed for the plain concrete, take the thickness of the plain concrete all around to reduce the area to reach this new area. And we said that the relation between this length and this length is 2TPC. Okay, so this is what we have reached so far. To get the moment, we said that I need to calculate the actual stress, because when I chose these dimensions, maybe I increased it a little bit to get round figures, or I used plain concrete. In case of using plain concrete, so in this case, the dimension will be very much reduced. The dimension of the RC will be very much reduced. So in both cases, we are going to calculate the actual stress. To get the actual stress, I divide the ultimate load of the column by the area that I have selected. I selected an area, so I divide the load by this area to get the actual stress. I use this actual stress to calculate the bending moment. But now we need to speak about cost a little bit. To reduce the cost of everything, I can calculate the bending moment as being WL squared by 2. What is L? L is the length of the cantilever. Usually you may think that you would just take, for something like this, from here to here. I mean from here to here. This is L. But actually I need the moment at the edge of the column. It will be a little bit less. Why? Why do you take why not to take it at the center line? I mean, take this. This is the edge of the plain concrete. If I go inside a little bit here, the moment is W by this L squared divided by 2. If I go a little bit inside, the moment will increase till it reaches the maximum at this location, at the edge of the column. Once you go inside the column, the section has changed. It is not a normal foundation. It's a foundation with the column from. It's a different case, and it will be very safe because the column it increases the stiffness of this section, the rigidity of this section. It includes reinforcement. It includes many things. So the critical section is the section at the edge of the column. So instead of using this bending moment here, please calculate it here. It will be less. And less means less money. So this is, so once you get the F actual or the actual stress of the from the soil, you get the bending moment, which is the moment using the shorter L, which is reaching till the edge of the column. So once you get this M actual, then you have to calculate it twice. Once for this direction and another time for the long direction and for the short direction. If you have the same cantilever, length of cantilever, then you have only one moment to calculate. If you have different cantilevers, then you can calculate two and get the moment of the maximum moment from both. What I'm going to do with this maximum moment, I need to design a concrete section. Go to the concrete code, see what is the equation used to design a concrete section. I here presented an equation. D equal C1 root M ultimate by 10 to the power 6 divided by FCU by B. If you have a different equation that you are using in your RC lectures, please use it. Don't stick to what I presented here. So using this equation, you can use the maximum moment from both. Here we have M1 and M2. Take the maximum of them, put it here, put the B. In this case, the B will be this direct. Let's see, I need a plane. The B will be this dimension, this B. So you will get the D, the depth of your foundation. Of course, you are using the maximum moment, so this is the maximum depth that you require. Add the thickness of the cover, which is usually 7 centimeter in the Egyptian market. So add 7 centimeter to this D, then you get the number. Is this number will be taken as it is? No, because suppose that D that you have calculated is 41.2. and you will add 7 centimeter, so it will be 48.2. I cannot tell the people on site, I need a foundation of depth 47.2. It's nonsense. I will say 50. So this is what then we will have to recheck again. Why to recheck again? Because once we have reached this T, we have to adjust it again. Because why are we going to adjust it again? Because there are some checks that we have to calculate. Usually I'm getting the D to calculate the area of steel, but before calculating the area of steel, I need to check that the concrete is safe under this depth. So before going into this case, I have to check shear and I have to check punching. We will not discuss this in this part of the lecture. We'll discuss it in the other part. But I have to check shear first and check punching first. And if they are unsafe, I will increase the depth. So I will come to this equation again and use a bigger depth and so on before calculating the amount of steel. So don't go after calculating the D, calculate the amount of steel and then check, because if it is unsafe, you will recalculate the steel. So you have to calculate the steel once you have reached the fine. To end this part of the lecture, I have just to give you an introduction. What is the difference between shear and punching? Do you know what is the difference between shear and punching? This is very important to feel the sense of what is the difference between shear and punching. They are both stresses. What is the difference between shear and punching? If I give you a bar of chocolate and I want to give you a piece of this bar of chocolate, I will just use my finger and take the corner and just bend the corner. Once I bend the corner, part of the chocolate of the bar will be separated. I will give you this part. In this case, I sheared the bar of chocolate. But if I put the bar of chocolate on the table and I put my finger on top of it and I press on it and my finger penetrates the bar of chocolate, then I punched the bar of chocolate. So shear is part of the foundation leaving the main foundation. But punching means the column pressing hardly on the foundation to shear the foundation, the column, all around the column, and penetrates the foundation. So this is the sense of what is the difference between punching and shear. They are both shear. It is all shear stresses, but in different ways. So the allowable here is different than the allowable here. So people from the RC department give us some codes and some equations to use. So we have to check that our foundation, when we put it on the ground, part of it is not going to be separated due to the load, and the column is not going to penetrate the foundation and leave the foundation alone. So penetrate means punch, so this is punching, and I compare it to a different value, a standard value that I cannot exceed. And for the shear also, I will check which is the critical section, which is the section that may be sheared. Is it just a corner or a portion from the length or a portion from the breadth? Usually, the bigger the portion, the bigger the force, and it will be the critical. So I just check the bigger dimension, and I try to get the bigger part that can be sheared outside the foundation. I check the shear of this one, and I compare it to the number that they have given me. If it is less, then it is okay. If it is more, then I have to increase the depth. This is what we are going to say in the next part of the lecture. So we can stop here and take a rest for a while. Thank you.